Hello everyone, welcome back to Math with Allison. Today we're doing something a little different again, so we're going to go over another exam. So this is a real Calculus 1 exam from the university that I'm a graduate student at. The professor gave me permission to make a video about it, so if you want to look at the exam before we go into the video, the PDF is linked directly down below in the description, so you can try it out, or you could write on it directly if you want to go through this video with me, whatever your heart desires. But this is now given to students as a preparatory exam for their actual exam. So this was given in 2017. It's a bit old, but the formatting of the exam is still very similar. So let's go ahead and go through it. Looking at this initial page, we can see that we're going to have a total of 11 questions. And it also gives the point breakdown, which is super nice. So let's go ahead and dive into it. There you go, I zoomed out so we could see the whole thing. But first, we're given a graph of a function, and it's asking us to find all the different parts of the limits. So let's go ahead and do this thing. First, we're going to go ahead and look at the limit as x approaches -2 from the left side. So if I look at -2, it's going to be this value right here, and we're going to approach from the negative side of that. So that's going to be this function right here. And as we can see, it's approaching a value of 4. And so that's what I would fill in for part A. Now we want to look at the limit as x approaches -2. And when a side is not indicated, so we can see right here there's no side given, that means we're going to look at both sides. So we already looked at the left side, so let's go ahead and look at the right side. I can see if I approach from the right side, I'm approaching a value of 0. So since I'm approaching two different values, 4 and 0, that means my actual limit is not going to exist. So we write does not exist. It cannot be two values at the same time. So now the problem is asking us to find where the function is actually defined at -2. And that is going to be wherever our hole is filled in. So in this case, at -2, we're going to be filled in right here, which is a value of 4. Okay, so now we're going to go ahead and look at the value 0. So let's go ahead and find 0 on the graph, which is going to be this line right here. And we want to take a look as we approach 0 from the right. And as we can see when we go down, we're going to be approaching a value of 2. So I'll fill that in. Now we want to take the limit as x approaches 0 from both sides. Let's go ahead and make sure it's approaching the same thing. If I look from the left side, I can also see I'm just approaching a value of 2. And so that means my limit is going to be 2. Now f of 0 is going to be where the function is actually defined. That's going to be where the hole is filled in. And as we can see, the hole is filled in right here at a value of 5. So that's going to be my f of 0. Alrighty, so the question is f continuous at x equals 0? And our answer is going to be no, it is not continuous because we have a jump discontinuity. The function jumps up, or we can call it a removable discontinuity, but there's a hole where the function is defined somewhere else. So that means I have to lift my pencil. Now, is f continuous at x equals 2? If we look at x equals 2, that's going to be the value right here. And we can see that this is going to be continuous. I don't need to lift my pencil at all. The limit is going to be the same as the actual plugged in value. So here I would write yes. Alrighty, let's go ahead and move on to the next problem. So here we are given another graph. We have y equals f of x. And again, we want to go ahead and find these different limits. So let's go ahead and look at our first limit, part A right here. We want to look at the limit as x approaches -1, which is this vertical asymptote right here. But we're going to be approaching from the left side, so the negative side. And as we can see, we go down to -infinity, right? We want to look at the right side of -1, and so I'm going to be going up this way and approaching a value of positive infinity. So now we're going to take the limit as x approaches, that's supposed to be an arrow, -1 from both sides. When they approach different infinities, so negative and positive infinity, that means we're going to have a limit that does not exist, so D and E. Whenever we approach two different values, that's always going to be the case. But now we want to take the limit as x approaches +1. So let's go ahead and find +1 on the graph. I can see that is the vertical asymptote right here. And remember, when there's no side indicated, we need to look at both sides. So on the left side of 1, I can see I'm going up to infinity. And on the right side of 1, I'm also going up to infinity. So even though there's an asymptote here, because they're approaching the same value of infinity, that means my actual limit is going to be approaching infinity. So now let's go ahead and define the asymptotes. So horizontal asymptotes are associated with end behavior, and that's the limit as x approaches positive infinity and negative infinity. So let's go ahead and look what happens when x approaches negative infinity. That's going to be my end behavior over here. And it looks like we're approaching a value of 0. Do we see how we're approaching the x-axis? Now when we take the limit as x approaches positive infinity, again, my function is going to be over here, and it looks like, again, I'm approaching the x-axis, which is a value of 0. And so that tells me I'm going to have a horizontal asymptote at y equals 0. So remember, when you're looking for horizontal asymptotes, look at the end behavior. Vertical asymptotes, they're very much more clear on this graph. They're given by these blue dotted lines. And so it's just going to be all the asymptotes where the function is not hitting that value. So here we would have x equals -1 and +1. You could write and, you can write comma, both of those are correct. So let's go ahead and go to problem 3. Now I can zoom in. Okay, so now we're going to go ahead and evaluate limits. So when we do so, always try using direct substitution first. It sometimes saves us some steps. So if I were to plug in x is equal to 2 into my function here, I get 2 minus 3 over 2 squared minus 9. That is equal to -1 over 4 minus 9. That's -1 over -5, which equals +1 over 5. So using direct substitution, I didn't need to worry about solving this out like at all. Okay, so now let's go ahead and try direct substitution again. We're going to plug in a value of 3. So I get 3 minus 3 over 3 squared minus 9. I can see we're going to have some issues here, and I'll go ahead and solve this out, and we get 0 over 0, and this is super illegal. Typically, when you see 0 over 0, there's going to be a way to simplify the function. So I'll go ahead and rewrite it. Okay, so if I look at the denominator, I can see I can factor it, right? It's a difference of squares. So in the numerator, I have x minus 3, and in the denominator, I'm going to factor that into x minus 3 and x plus 3. And now we can see one of those factors cancels out, right? And so now I'm left with the limit as x approaches 3, and that's going to be 1 over x plus 3. Now we can go ahead and use direct substitution. I can just plug in that value 3 to our new function. So I get 1 over 3 plus 3, which is equal to 1/6. And that's our solution. So here we use factoring, and this method is called factor and cancel. So let's go ahead and try part C here. First, we're going to want to try direct substitution. So when I do that, I get -3 minus 3 over -3 squared minus 9. We can see there's going to be an issue here. That denominator is going to be 0. And again, super illegal. We don't like to work with dividing by 0. So in this case, notice it's a little bit different than the last problem. We got 0 over 0 in the last problem, which means there's a way to simplify it probably. If we try to simplify this out, right, we would end up with 1 over x plus 3 because it's the same function. And again, if we plugged in -3, we would still have 1 over 0. So this means that x equals -3. X equals -3 is a vertical asymptote. So that means we need to take the limit as x approaches -3 from the left and from the right in order to see what's going on here. Alrighty, so let's go ahead and see what both of these are approaching. The numerators are not going to change when we plug in -3, so they're both going to be approaching a value 1. But now let's go ahead and see what our denominator is approaching. So let's take a number just to the left of -3, so maybe -3.1, and we're going to plug that into the denominator. So -3.1 plus 3, this is equal to -0.1. So this tells me my denominator is going to be approaching a small negative number. So when this happens, we have a 1 divided by a small negative number. That's going to shoot down to -infinity, right? A vertical asymptote means that the functions are going to be infinite, but we don't know if they're going to the same infinity or different infinities. So that's what we're trying to figure out with this. Let's go ahead and try a number just to the right of -3, so maybe -2.9. We can plug that into the denominator, -2.9 plus 3. This is going to give us positive 0.1. So again, this is going to approach a small positive number, which tells me the function is going to shoot up to positive infinity. So notice here that they are approaching two different infinities, which tells me that the limit as x approaches -3, this is going to not exist. So we write D and E. And that's because they approach two different infinities. Alrighty, problem 4, we're going to have some one-sided limits. So we have to be careful with our function here. Notice that we have a square root function. When we have a square root function, we have some illegal values, and that's we cannot take the square root of a negative value. So we do have to be careful of that. When we plug in a value of 2 when we try direct substitution, that's not going to give us an issue yet. So if we plug that directly in, we get 2 minus 1. This is equal to the square root of 1. And then taking the square root of 1, we end up getting positive 1, right? So that is going to be what our limit is approaching. Now we want to take the limit as x approaches 1 from the right side. So think about it in terms of the context. Can we plug in values to the right of 1? So in this case, yes, we can. And we can go ahead and just use direct substitution. And when I do that, I'm just going to take the square root of 1 minus 1, which is equal to the square root of 0, which is just 0. And that is our limit. Where we can get a little tricky is plugging in values that don't exist. So when we take the limit as x approaches 1 to the left, let me go ahead and draw out the function. That's my beautiful drawing right here. We're trying to plug in values to the left of 1, but I can't plug anything in. The function doesn't exist over there because then we would have to take the square root of negative numbers, which gives us imaginary numbers. We don't mess with that stuff. And so this is where we would write the limit does not exist, and we cannot use direct substitution. So we have to be very careful because some of these can be a little tricky. Alrighty, so now we have a problem on limits at infinity, and so we're taking the limit as x approaches positive or negative infinity. So remember, when we have a number divided by a really big number, so infinity, for example, this is going to go to 0, right? So if I use that method of thinking, that means this 2 divided by x squared is going to approach a value of 0. So if I were to use direct substitution, the 5 doesn't change because there's no x value associated with it, but it's going to be 5 minus 0, which is just equal to 5. And so that is our solution. Now, this is my favorite method. You can only use this if we're approaching positive or negative infinity, but it's where you take the biggest terms on the numerator and the denominator. So here I can see my largest term is going to be 6x squared, and in the denominator it's going to be 5x squared. And I can just rewrite my limit with just those two terms. The reason for this is when we plug in infinity, we have 6 times infinity squared plus 2. Adding 2 is not going to make much of a difference at a really, really big number. It's still just going to be a really, really big number. Same thing with the denominator. So that's why we can just take the highest terms at limits at infinity. And here we get to do some simplification, right? We know those x squareds cancel out. So I just left with 6 over 5. And the limit of a constant is just the constant. And so this is equal to 6 over 5. Now we can use that same method right here. We have 6x cubed in the numerator and then 5x squared in the denominator. And so when I rewrite that, I get the limit as x approaches infinity, 6x cubed over 5x squared. We can simplify that out a little bit, and we get 6x over 5. Now if I were to plug in infinity, I would get 6 times infinity over 5. Well, 6 times infinity is infinity. Infinity divided by 5 is infinity. And so this would be an infinite limit, and that is our solution. Alrighty, so here we're given a function, and we want to find the horizontal and vertical asymptotes. The thing that I always suggest first is to try to simplify it out a little bit. So I can't simplify the numerator, that one's stuck as is. But in the denominator, I can pull out a value of 3, and I'm left with x squared minus 4. Now I can see in the denominator I have a difference of squares. And the reason that I suggest simplifying it out is because you can see anything that cancels. Any terms that cancel are going to give a whole. So we don't have to worry about any holes in this case. We're just left with that. So let's go ahead and do part A here. We're going to find the horizontal asymptotes of f. And horizontal asymptotes are found at the end behavior. So when x is approaching negative infinity and when x is approaching positive infinity. And now we're dealing with limits at infinity, just like the previous problem. So we can take the largest term in the numerator and the largest term in the denominator. And we can do that on both of these limits. So next we can go ahead and simplify both of these, right? Those x squared cancel out. And when we take the limit of a constant, it's just going to be equal to that constant. So here we get 2/3 for both of them, which means we only have one horizontal asymptote, and that's going to be at y equals 2/3. Our options for horizontal asymptotes is we're either going to have two of them, and that's when the limits give us two different values. We're going to have one, and that's when the limits give us the same value. And sometimes we don't even have a horizontal asymptote, and that's when the limits are going to be positive or negative infinity. Alrighty, so let's go ahead and find the vertical asymptotes of f, and that's why we first simplified it out. So this is where we set the simplified denominator equal to 0. So here I'm going to take 3 times x plus 2 times x minus 2, set it equal to 0, and we're going to solve. So when I do that, I get two values. I get x equals -2, and I get x equals +2. And we want to look at what happens at those two values. So let's go ahead and take our function. So we have as x goes to -2, our function 2x squared plus 1 over, and I'm going to write our simplified version, x minus 2, x plus 2. We want to talk about what it approaches. So in the numerator, if I were to plug in -2, I'm going to do that work up here. I get 2 times -2 squared plus 1. This is equal to 2 times 4 plus 1, which is equal to a value of 9. So our numerator is approaching a value of 9, but since we set the denominator equal to 0, that's obviously going to be approaching a value of 0. And when you approach a value of 0 in the denominator, that means our function is going to grow infinite. So how we write that out is that this function grows infinite. And so now we can say that with our other vertical asymptotes. So as x approaches +2, our function, and we can show what they approach. That approaches a value of 9 as well. This approaches a value of 0. And we can say this grows infinite. I've also seen on exams where the professor, and it depends on the professor, wants you to find the limit as x approaches the vertical asymptote from the left side and the right side and show that they're infinite. Because here that shows that it's a vertical asymptote, but I've also seen this method. So it's going to be whatever your teacher prefers. Okay, so we have another problem here. We're going to talk about average and instantaneous velocity. So here we're given a chart. We're given the position function is s of t equals the square root of t. And so first we want to find the object's average velocity from t equals 0 to t equals 2. So if we remember how to find average velocity, we take our function s of 2 minus s of 0, and that's going to be over 2 minus 0. We can go ahead and just look at our chart, right? So s of 2 is equal to 1.41421. 2 minus 0 is equal to 2. This could potentially be enough, but if you needed to, you could always whip out long division. I cannot plug 2 into 1, right? So that's going to be 0 point. And now I'm going to pretend that's a 14. So 2 goes into 14 7 times. And again, 2 cannot go into a value of 1, so that's going to be 0, and I'm going to drop down the 4. And so now here, 2 can go into 14 7 times. So again, I can subtract that. Dropping down the 2, 2 can go into 1 time. So subtracting that out, I get 0. And now I can finally drop that last value of 1, which will go in 0 times. So I need to add a 0, drop it down. I would say that's probably good enough. I would also say that you could potentially end at this point. It's just, again, going to be up to the professor if they want you to do long division or not. Whatever your heart desires, I guess. So now we want to find a reasonable estimate of the object's instantaneous velocity at t equals 1 based on the chart above. So when we want to find the instantaneous velocity at t equals 1, we're looking at the rate of change of our position function. So here, let's go ahead and look directly to the left of 1. I'm going to take this value 0.99 with the corresponding s value. And of course, we're going to also take our values of 1. And it's like we're going to be calculating a mini average velocity. So I'm going to take v and set that equal to 1 minus 0.9995. And I'm going to divide that by the corresponding t values, just like we did for average velocity. So here I get 1 minus 0.999. And I just got that from the chart where I highlighted. So when I do that, I get 0.1235. And then this is going to be divided by 0.001. So in order to see what this is equal to, it's like you can just cancel out the zeros. And so here we get 0.5 divided by 1, which is 0.5. So now we're going to go ahead and do the same thing, but now on the right side of 1. So I'll take the value just to the right of 1, and of course we're going to be again working with the actual values of 1, and it's like we're taking those mini average velocities. Alrighty, so when I do that, I get 0.1235 divided by 0.001. So again, we're going to cancel out as many zeros as we can. I have 0.5 divided by 1, which is equal to 0.5. So this is going to be my reasonable estimate of the object's instantaneous velocity at t equals 1. So I'm going to write, and then the work I have is going to be the work that I showed, right? Okay, so now let's go ahead and go on to problem 8. So here we're given a list that defines continuity. If all three of these are true, then a function is continuous. And we're going to go ahead and answer these parts. So first A, at which values of x is the function discontinuous? So remember, this is going to have to be where you lift your pencil. So I'm just going to go through it like I'm drawing with my pencil. I'm looking pretty good. I'm continuous. Oh, it looks like I hit my first discontinuity, which is going to be this jump right here. So first we have a discontinuity at x equals 0. Let's go ahead and see if there's any more. I'm going to continue going forward. And then boom, I hit another discontinuity. And that's going to be because I jump all the way up right here and then continue on forward. And so I'm going to have a second discontinuity at x equals 2. Part B, at which values of x is the first condition violated? So are there any values where f of a does not exist? So again, looking through, it looks like I'm existing. I continue existing. I do exist at x equals 0, so I'm good there. Continue existing, and at x equals 2, I have a filled in hole, and then I continue existing. So there's actually going to be no value, so I'll write out none. C, at which values is x is the second condition violated? So that's where the limit does not exist. The limit does not exist when the limit from either side do not approach the same value. So if we look at x equals 0, we can see on either side of the limit, we approach the same value, which tells me my limit exists. So x equals 0, we're good. Let's go ahead and look at x equals 2. On the left side, I'm approaching a value of 1, but on the right side, I'm approaching a value of 2, 3, 4. It looks like 5. And so here, that is going to be where my second condition is violated. My limit does not exist at x equals 2. Part D, at which values of x is a third condition violated? So that's going to be when my limit does not equal the actual value. So a great example of that is going to be at x equals 0 because my limit is approaching a value of 5, but my function is actually defined at a value of 4. So for sure at x equals 0. Now let's go ahead and take a look at x equals 2. My limit is going to not exist, and not existing is definitely different than a value of x equals 5. And so again, I'm going to violate that condition at x equals 2. Alrighty, so now we're going to consider this piecewise function, and we're going to use the list from the previous problem to analyze the continuity of f at x equals 5. So let's go ahead and look at the checklist. Part 1 is f of a defined. So let's go ahead and go down. We're going to write out part 1, and we're going to say f of 5. And let's go ahead and see what that's equal to. That's going to be defined when x is equal to 5, and our value is going to be 10. So this is going to equal a value of 10. So we're good for part 1. Let's go ahead and move on to part 2. The limit as x approaches 5 of f of x needs to exist. So let's go ahead and take the limit. So when we're approaching 5, we're not actually equal to 5. So now we have to pay attention to when x is not equal to 5, which is going to mean we're going to have to use this part of the function. So here I'll fill that in. So if you'd like, we can first use direct substitution. So when I do that, I get 5 squared minus 25 over 5 minus 5. This is going to be equal to 0 over 0, which is illegal, not allowed. But notice it equals 0 over 0, which means there's some way we can simplify it. We can see that the numerator can be separated into two factors. So we get x minus 5, x plus 5. If you initially saw that, you don't need to use direct substitution. You can just plug it in. And here we get the x minus 5's cancel. And now we just have x plus 5. So let's go ahead and evaluate the limit. I'm going to plug in that value of 5. So I get 5 plus 5, which is equal to 10. So here we have the limit as x approaches 5 of f of x is going to be equal to a value of 10. Alrighty, so now to look at part 3, let's go scroll up. The limit has to be equal to where the function is actually defined. So that means we're going to set part 1 and 2 equal to one another. So here we have the limit. This was equal to 10, and this was also equal to f of 5, right? So we have all three conditions are satisfied. So f of x is continuous at x equals 5. Let's go ahead and move on to problem 10. So problem 10 and 11 are true and false questions. So we have the value of the limit as x approaches a of f of x is always found by computing f of a. The answer here is going to be no. We do need to give explanation for our answer, so we could write out why, or we could just give a counterexample. And I always suggest giving a counterexample by drawing a picture. So let's go ahead and pretend we have a function right here, and let's go ahead and find a hole. So I'm going to set a hole right here, maybe at x equals 3, and I'm going to fill in that hole higher up. So I'm just deciding random numbers, right? So here, if this is f of x, we have f of 3 is actually defined at 5, but the limit as x approaches 3 of f of x is going to be approaching a value of 3. And we can see that these are not equal. So the value of the limit is not always found by just computing f of a. So I suggest drawing a picture. You could also draw a vertical asymptote if you wanted. You could also explain yourself. I think drawing a picture is nice, but that's just me. Alrighty, one more problem. So here, the graph of a function can have at most 2 horizontal asymptotes. So let's go ahead and remember how we find horizontal asymptotes. We take the limit as x approaches negative infinity of our function, and we take the limit as x approaches positive infinity of our function. Notice here, there's only 2 limits. That means there's only 2 horizontal asymptotes maximum. So this is going to be true. We look at the end behavior of the function, and there's only 2 maximum possible outcomes for end behavior. So like I said earlier, we have 2 horizontal asymptotes if these 2 limits are different numbers. We have 1 horizontal asymptote if these 2 are the same number, and we have 0 horizontal asymptotes when these are equal to infinity. So like it says, you need to give an explanation. So if you wanted to explain yourself, you could write out what I just said. You could do the limits right here that I have written out. Whatever you're thinking, you could write out, but our answer is going to be true. So that's all I have for us today. If you enjoyed this video, I have many more like it, so make sure to check out my playlists. They're linked directly down below. Otherwise, please give this video a thumbs up and comment other videos, problems, topics that you'd like to see done. Thanks for watching.